The last presentation of this session, I will be delivering it on the behalf of my former PhD student, Mayura, at the University of Ottawa, so entitled A New Proportioning Framework to Increase Performance While Decreasing the Carbon Footprint of Concrete. So I think I'm going to be brief on this one. Everybody knows that we need to decrease carbon footprint. We've been discussing a lot on that. I think people tackle a lot decrease of cement, which is definitely the way to go. But how do we play with aggregates in that perspective too? So this is what I'm going to try to present partially to you. So the concrete is being used more and more, what we are going to do, all of that, blah, blah, blah. So we have actually 7 different strategies, I would say, to try to tackle that problem. So savings in clinker production, savings in cement and binders, we have carbon capture, we have efficiency in concrete production, decarbonizing of electricity, CO2 sink, and efficiency in design and construction. So in this work, what we are going to try to show is that through selection of raw materials and better mix proportioning, what we can do is we can tackle 3 of them. So efficient in concrete production, cement and binders, and finally construction, because construction depends on the fresh straight properties for application and so on. We can tackle at about 42% reduction if we work properly. So nowadays in practice in the market, what do we got? We got normally very descriptive tables, such as for instance ACI proportioning method, in which you select the amount of the slump you want. Depending on the exposure you get a given strength, which is related to a given water to cement ratio, and there is a requirement depending on the type of element, it's a flat work and so on, the minimum amount of cement. So this is more or less what we have in practice now. However, I like pretty much this plot here that has been generated in 2014, in which every single dot here represents the BI factor, which is amount of Portland cement used to get 1 unit of property, in this case compressive strength. And we see that, you know, people use lots of cement for very conventional concrete. So the way I read this plot is the following. You see that there is a downward trend like this. So concrete mixtures that present a moderate to high compressive strength, they are kind of much more optimized than mixes that we normally use for critical infrastructure, let's say 20 to 40 megapascal, in which we use lots of cement to get relatively low strength. So we need to go to try to optimize that perspective. And if you do an average, you're going to see that you know, we are using amounts of Portland cement in our mixes that go above and beyond 420, which is huge. So what's our goal? Our goal is to try to reduce it and still keeping performance. And of course, respecting this triangle here, which is hardened state, fresh state, and durability. But moreover, perhaps including a 4th term, which you presented exactly the same figure, which is no longer only look at these 3 guys here, but actually tackling the sustainability aspect of all that. Okay, so what can we do in terms of saving of cement? I mean, there has been a very important shortage of supplementary cementing materials. People are discussing, if you go to conferences in North America, Europe, South America, and so on, depending on the places, they are tackling different alternative materials, different SCMs, and so on. But if you look at this chart here, we can see 2 things. We can see that there is an opportunity with calcined clay, in which many people in Europe, they are talking about that, the LC3 and this type of cements. But we can see the very good opportunity of usage of limestone fillers too. They are widely available worldwide, and we could try to tackle its use a little bit more frequently. Which, by the way, I think there has been a question in one of the previous presentations regarding that, and in Europe they use 35% or more already in the types of cements, but again we can further discuss that later on. But not only a replacement of the material, because we are very used to hear that, oh, this is green concrete. You simply get your same mix, proportioned by a very conventional method, you replace Portland cement by, I don't know, a slag or something, in a given percentage, you'll say, well, this is green concrete. But we can do better than that. We can, instead of just replacing, we can find a more intelligent way, and I think Konstantin and other colleagues, they presented already methodologies for doing that. In our work at the University of Ottawa, we are very interested in packing things, but I agree 100% with Konstantin. We are not only thinking about packing without thinking on the distance between those particles, because if I pack too much, I don't have rheological behavior of interest. So just packing is not the end of the story, but it's actually rather a combination of packing and actually detaching the particles so that I get flow. So what is our approach on this? So we decided to do a continuous particle packing model because I think Konstantin also mentioned that gap grading is sometimes doable, sometimes even intended for, depending on the applications, but it's not really real life. So we use the modified Andreasen model, or the so-called Alfred model, that it's a very simple equation in which you have a Q factor, which is the packing factor. The higher the Q factor, the more fines you have in the system, or the more powders. With that methodology, the universe, if you wish, of Q factors, they go from 0.21 to 0.37, in which the 0.37 is the guy that generates the lowest dry porosity. It's important to notice here that here we are just talking about the dry packing, that there is no water in the system. But if we go for a concrete with a Q factor of 0.37 here, we are kind of getting I would say, a roller compacted concrete, pretty much very, very dry. Whereas if we go towards very low Q factors, we are going to go for more self-leveling systems. So our approach developed by Maira is that the model worked for some concrete mixtures, but not all of them. And trying to decrease carbon footprint, but also improving performance, we decided to change a little bit the previous equation and break it. So our approach is to get, if we come back to this cumulative particle finer than, we go from 0% to 100%, and the model tells you how much, in terms of percentage, of the sizes of the particles you need to have, depending on the behavior in the fresh state you want to got. However, what we want to do here is to break the curve and divide a first analysis of powders and a second analysis of aggregates. And it's worth noticing that for us, powders is anything that is below 100 to 150 micron. So basically, we optimize the binder phase, and then we optimize the aggregates phase, which comprises fine and coarse aggregate. Normally, what we finish by doing is to try to use something as close as possible to 0.37 in the powder phase. And why? Because then we were going to reduce the amount of fines in the system, and then reducing cement, which is good, right? But then we need to adapt the coarse phase, meaning fine and coarse aggregate, so that we get a rheology of interest. And how can we get, is this possible to get the rheology of interest already looking at that plot? Unfortunately, it's not. So we need to couple that initial model with a secondary model that is called mobility parameters. Mobility parameters are, actually, there are two indices, the IPS and the MPT. Basically, they measure the distance between particles that are lower than 150 microns or 100 microns, and particles that are coarser than 100 microns. So basically, my idea is to pack, but pack in such a way that I can control the distance between the particles so that I get a rheology of interest. So this is, our concept. So another thing of interesting is that to do that, we need fillers. And then we can discuss if they are going to be limestone fillers, other types of fillers, but not only a conventional filler with a particle size distribution as this one purple, for instance. Portland cement is the green guy. So you can see that we can pretty much replace without paying attention. But one of the issues I see whenever we talk about proportioning is that people say, well, I replace 10%, 15%, 20%. but perhaps the particle size distribution of the filler you are using is not necessarily the particle size distribution of your Portland cement. So you cannot replace one by one because it's going to change rheology, it's going to change packing, and so on. So our approach is to try to use two types of fillers, a filler that represents more or less, or as close as possible, I would say, the particle size distribution of the cement, so that you can change by percentage pretty much, but another one that is much finer, and then you can try to improve performance. So in this work, what Mayra tried to do was the following. First of all, she designed a conventional mix already with a not that much high carbon footprint, so 320 kilos per meter cube. And then we decided to do 3-pack ppm mixes, right? With 2,050 kilos per meter cube, 200 kilos per meter cube, and 150 very low kilos per meter cube. It's important to notice here that since we're trying to benchmark our approach, we didn't use any type of supplementary cementing materials, meaning that our mixtures could have been even improved if we could have used supplementary cementitious materials. And then, of course, we know that is lump and is a very preliminary, besides strength, parameter that people need for practical use. What we said is that for each of those type of concretes, you're going to follow the required slumps as per ACI documents. So let's say 120, more or less 20 millimeters, 90, and a very dry 20 millimeter concrete for all of those mixtures. It's important to notice that we selected water to cement ratios well, first of all, let's put that way first. They look weird, the water cement ratios. They are kind of high. And I think someone mentioned here, perhaps in one of the earlier presentations, that the conventional Abrams law and the conventional world of water cement ratios that we normally use for ACI design and mixtures and so on, from 0.4, 0.45, and so on. There's even standards in Canada, for instance. If you are C1 exposure, you cannot use above and beyond 0.4. So for this type of packed concrete with limestone fillers and so on, we can get performance with very different water to cement ratios. So this is one of the discussions I was having with Mayra, is that once we prove that we can go and get performance out of it, there is a second battle, which is to be able to standardize those guys, because they're completely out of all of the standards existing in the world. But anyway, we try to keep the same water cement ratio to fix the same microstructure, so that we can compare apples with apples. And another thing is that we try to fix the same water to powder ratio, so that we could control the distance between the powder particles and then control workability in general. So basically what we have done, the water to fines or water to powder ratio, we fixed into 3 different numbers that would provide us IPS, if you recall, the measurement between the powder fractions, and MPT, which is the distance between the coarser fractions, in ranges that we could correlate then with rheological behavior. Okay, so let's show you some results. So first of all, it's very important to show with slump results, because everybody uses that in practice. I think the message here is that we were able to get all of these lumps required for all of the mixes with or without packing. The amount of superprocessizer, of course, increases a lot with reducing cement and even though if we are packing the systems. But we found a very interesting property here, is that similar amounts of admixtures were needed for the same distance of particles. So it looks like that here we are trying to understand behavior. We kind of understood that, you know, if we are able to set the average distance between the coarse particles, we could try to create a model that could allow us, for a given amount of cement, to know the amount of admixtures required to get a given initial slump. So that was very interesting, and I think we need to keep digging on this process. Besides that, another thing we have done, just to check, because we thought that that might have been an issue, was the slump loss over time. This is very practically speaking important for concrete suppliers. And we could see that, you know, if you decrease the amount of cement, unfortunately, we're going to have a higher loss, and of course, increasing the amount of fillers as a function of time. So this is something that we will need to pay attention if we go towards that perspective. But more importantly, that is slump. Another thing that we realize is that normally people characterize in a global way workability of concrete just based on the slump, and there are several colleagues that are rheology experts trying to fight to get the thing properly discussed. So you see, we have more or less initial slumps, but we have very different rheological behaviors of the mixture. So we have a rotational rheometer in-house, and we were able to test torque as a function of the rotation for all of those mixes. So here you see the ACI mix. Here you see our 250, 200, and 150. So basically, the initial point here in the y-axis curve is the initial slump, if you want, that we call also yield stress. And the blue guy is a 0, just measured after batching, whereas we measure 15 minutes after and 30 minutes after. So again, as we can see, for the slump loss is the same. So we keep going up in the y-axis for the initial torque. So we need a little bit more energy to enable flow, which correlates 100% of that. But nicely enough is that all of the mixes, they presented a shear thinning. Because normally we say that we need a given slump, or we need a given amount of binder or amount of cement to get concrete pumped or well vibrated in the field. But sometimes the viscosity increases as a function of the torque. As you know, we have lots of torque to be able to pump or to vibrate. So what we don't want to have is a shear thickening behavior, which goes increasing, which would be a convex shape, completely the opposite of this. This one, actually, I have a decrease in viscosity as a function of the torque applied, meaning that it would be a very good concrete to be vibrated, even with a very low amount of cement and very high amount of fillers. Now, talking about hardness state, compressive strength, the first thing we could see is that the water-cement ratio governs, right? So the lower the water-cement ratio, the higher the strength, as we could already, it's very basic. But the use of filler, not only the use of filler, but the use of the particle packing model you see here, 250 compared to the 320 without fillers, we can have a 20% increase in compressive strength on average, which is very, very good. But this doesn't come just because of the filler. It's important to notice. It's because of the mix, packed and well proportioned, in the presence also of limestone fillers. If we look at our ppm mixtures, it's important to notice, if you look at the water-to-cement ratio of the 150 to get the initial slump that we required for this, they finished by being really high, and because of that, they were very ordinary concrete. But the vast majority, I would say 5 out of 9, for mixes going with 200 kilos per meter cube and above, 250 and of course 320, they were above and beyond 30 megapascals. So without any type of supplementary cementing materials, without any type of optimization of water-to-cement ratio to get any type of strength, again, we were trying to simply benchmark our approach to pack and to proportion those mixtures. Modulus of elasticity. So modulus of elasticity is extremely dependent on the aggregate, right? For conventional concrete, the strength of the concrete is secondary in that perspective, but of course we can see a slight behavior, a slight increase as a function of a decrease of water-cement ratio, as we could see. But interestingly enough, all of them were above and beyond, except the 150 kilos. All of them 200, 250, and so on. They were above and beyond the 25 gigapascal, which is normally what is required and what we use for concrete members. In this case, we used limestone coarse aggregate and a natural sand. So we didn't play with different types of lithotypes of aggregates to try to get different values. We also tested the wet porosity, so capillary porosity via vacuum systems, and we could see that the ranges of our ppms, they are between 8 and 6. This is definitely not the total porosity in the system because we didn't do any type of mercury intrusion and so on. This is the capillary porosity, the ones that we can measure via drying and wetting under vacuum. But this looks like that we are reducing cement, and our porosity, our microstructure is becoming better. So that's very, very good news. So with all of those things, what we proposed, and that was amongst the endpoints of my year's PhD is to have a performance-based approach, so which is not necessarily related only to the descriptive methods, or we need a water dosimetry ratio, we need this or we need that, but are we getting performance out of those water dosimetry ratios that are required? So I believe that we need something that is more dependent on performance. And then, of course, we can discuss which type of performance we need for different mixes. But basically, this framework that we propose allows us to have this three-quadrant type of mix, in which here we can control strength as a function of the water dosimetry ratio, very simple. Here we can control the ranges of slump we got, so that we use a given amount of aggregates in the system and a given amount of packing, so that finally, and more importantly, towards sustainability, we control the third quadrant here, which is the amount of cement. Moreover, what we have done, this project allowed us to develop some models to predict performance and performance in terms of, let's say, compressive strength. So we realized that mixes that are fully or very packed and present an important amount of fillers, just the water to cement ratio is not enough to describe behavior. So we need a K parameter here, and that K parameter is actually reflects the amount of powder you have in your system that indirectly, if you want to think on Constantine model, for example, is already taking into account the packing of the fines. And of course, it depends on the hydration. You know, the more you need to get your hydrated products, it's something that evolves over time. So we were able to get a model that was good enough. There is an envelope, of course, because it depends on so many things, but that was good enough to predict the behavior of all of the mixes we proportioned with and without actually particle packing. Moreover, a very interesting thing we discussed is that the strength and other properties too, but the strength is actually related to not only the distance between the powders or the fine particles, but the distance between the cement particles. And then we created an index that is called IPS cement, which basically gets, instead of the distance between the powders, the distance between the cement-made powders. And we were able to come up with this model, and this model worked fairly nicely for all of the mixers we have used so far. So this was a 4-year project, initial project. Of course, we have, you know, the horizon is nice, but we have plenty of things to do. We can use different types of supplementary cementing materials. We can try to optimize water to cement ratios for different applications. We can try to optimize the rheological behavior and viscosity for different applications. But this showed the opportunity we have here to use better mix design approaches to get much better performance, decreasing carbon footprint. So finally, it's important to come back to that initial plot where I showed you, remember the 420 we were here, and the industry, normally we use the red dots here. The 3 black dots are dots that were obtained through the ACI method. So whenever we proportion with ACI, just following the tables and so on, we get these 3 black dots. All of the mixtures we proportioned ourselves, they were below or aligning to this 250 kilos per meter cube, so we could decrease the so-called BI, so the requirement of cement content to get 1 unit of property or 1 unit of compressive strength. And then Mayura decided to also calculate, as the previous speaker showed us, the global warming potential, and there is a table that was provided by Professor Valevik in 2014, in which several categories of concrete are related to the numbers here. So for instance, if we do the ACI method, we are about 300 here, whereas if we go towards the PPMs, we start decreasing below 200 and 150. Of course, this is completely related to the amount of cement used in the system, and the aggregate packing can help us to go towards lowering the global warming potential. So, in conclusion, on the one hand, most of the supplementary cementing materials that we are using are getting shortened, so we need to find other solutions. There are good opportunities with the use of clays and fillers, especially limestone fillers. We can develop eco-efficient mixtures with distinct slump ranges. Sometimes we feel like, oh, we are reducing cement, we are taking out the lubricant on the mix and so on, so perhaps we cannot reach levels of flowability. This is not true, we can. We have an impact on the decrease of cement, so we need new laws with the usage of fillers, laws that correlate properly with mechanical performance, which were initially developed here, but generally we were able to reach 20 to 45 megapascal without that much of a problem. And all depends on the quality of the microstructure, which can be measured by different means, such as porosity and et cetera, et cetera. So this was what I had to say. If you have any questions, I'll try to take it. Thank you very much.